Hi everyone, I am Fawad from Shenzhen Institute of Advanced Technology, Chinese Academy of Sciences. Our paper is Safe Reinforcement Learning for Object Manipulation in Safety Critical Coordinated Tasks. In the field of robotic manipulation, autonomous agents in existing systems have traditionally prioritized task performance, often treating safety constraints as secondary or neglecting them entirely. However, with the increasing deployment of robots in public and industrial settings, safety-aware operation is becoming just as critical as task performance. This paper presents a data-driven, closed-loop grasping approach for object manipulation, leveraging simulation data to ensure adaptive and safety-aware operation. We model our problem as constrained Markov decision processes through hierarchical reinforcement learning. We have proprioceptive information, which include the n effector position in Cartesian space, such as x, y, and z position. And tactile feedback we get it from pipelet physics engine as force and collision sensors. We have a policy network. We compare the standard PPO with its constraint variant cPPO and compare the performance with set exploration. We have the robotic arm itself as environment, so the agent get observation and make a decision based on the observation. Our problem is model is two objectives to maximize the rewards as well as to minimize the cost. So in the traditional reinforcement learning, majority of the work is conducting to maximize the reward and upon neglecting the cost metrics. So safety is crucial for advancing autonomous system. So DRL's adaptability makes it powerful for dynamic decision making, especially in robotic manipulation. Simulation environment in RL often lack the precision required for real-world transfer. So modeling human-robot interaction is challenging, requiring high simulation fidelity to capture sensitive dynamics. So this is how paradigm shift to learn the controller directly in the real world. The key challenges we can have unpredictability of real-world environments, risk of unsafe outcomes in real-world training. We build upon on the safety gym. Safety gym was initially developed for mobile agents. We incorporate the Panda robotic arm for object manipulations. Novel approach we introduce is grasp mechanics, which include the 3D translation control with text orientation for common household objects, adaptive motion planning, and real-time feedback, closed-loop grasping using proprioceptive and tactile feedback. Zero-shot generalization, our system is generalized on unseen objects. So the system is zero-shot generalized. Let's walk you through our methodology. Safe reinforcement learning through constraints. We model the task as constraint Markov decision processes. The agent goal was to maximize the reward while satisfying the safety constraints during both training and deployment. So in our case, when the robot makes contact with the obstacle, the cost is equal to 1. Otherwise, the cost is 0. So di is the threshold, which is ranging from 1 into k. So in our case, the di is equal to 1. Over here, we have some notations. We compared the PPO, the Proximal Policy Optimization baseline with its constraint variant, cPPO. We have the grasp mechanics, which help in tactile effects, which is mimicking how humans interact in the real world. So we have action, probability of action or state distribution. Given the state, the agent take the action. Core algorithm, we make use of PPO with its constraint variant. We make use of Lagrangian multiplier. So as we discussed in the previous slide, if the robot make contact with the obstacle, the cost is equal to 1. Otherwise, the cost is 0. We build upon on the safety gym. We make use of inverse kinematics, which reduces action space from 7D joint to 3D motion, enabling faster and safer learning. This implementation enhance policy generalization and facilitates sim-to-real transfer. We have a multi-step dense reward system, which is directly proportional in reduction to distance. So when the when the distance between the object and the robot decreases, the reward was increasing. We have context stability reward. We have left in collision penalty. So model architecture and training, we make use of PPO and PPO Lagrangian. We have state input. We also have tactile feedback, and we have state information, which is a dimensional vector, which include the robot and effector position, object position, and the finger status. So over here we have the observation space, the end effector position, the finger status, and the object position. So a total of, we have a dimensional vector, we have two hidden layers, each consists of such a polygonals. We have policy network, we have action distribution was state, we have tactile feedback, which we have studied in grasp mechanics. Experiment design and realization. Key insight. Increasing state vector dimensionality does not significantly improve learning for adaptive grasping. However, we introduce the grasp mechanics as a feedback greatly boosts learning efficiency and grasping performance. We compare PPO and cPPO algorithm. cPPO achieves lower average cost, safer training, slightly longer training time. Constraint optimization improves robustness and safety compliance. So we compare PPO and cPPO in terms of reward maximization and cost minimization, as shown in the table, the algorithm PPO and cPPO respectively. Discussion and conclusion. Enable safe and effective robotic manipulation in dynamic environment through constraint reinforcement learning. Key insight, we introduce grasp mechanics, closed-loop grasping approach for common household object. We make use of proprioceptive information and tactile feedback. Main results, safety cost reduced from 13.11 to 10.96 with cPPO, 89% success rate on unseen object. The policy is fully generalized. Insight from learning curves, cPPO converged within two case tips. Trade-off observed training stability with versus constraint enforcement. So future limitation, use text orientation, limit sensitive grasping. So the agent can grasp the object from top-down view. It was challenging for the agent to grasp the object from side view, like a shampoo bottle. Lack visual feedback may struggle with complex geometries. Future direction, expand to full 6D control using hierarchical policies. Apply teacher and student frameworks. So we would make use of knowledge distillation. Teacher set proprioceptive policy. The student we should learn through vision-based learner. So real world impact. Proprioception-based policy with tactile feedback show better sim-to-real transfer by avoiding the reliability logos date vision-based system. Thank you for listening. Questions are available.